So this is Unit 1, Lesson 11 of the AP Calculus course. The unit is called Limits and Continuity. The lesson is called Exploring Types of Discontinuities. And so this will be the beginning of our conversation on continuity. What we are going to learn in this lesson are classifying different kinds of discontinuities we might encounter as we work with functions. So three basic types of discontinuities. We have removable discontinuity, infinite discontinuity, and jump discontinuity. And so let me just grab this highlighter real quick. Whoa. All right. So removable discontinuity is when I could insert a dot at this point right here. So this is our hole in our graph, and this is where we lose. This is our point of discontinuity. If I plugged in 1 point, or if I define the x value, I could remove this discontinuity by filling in the point. Infinite discontinuity is when you have basically a vertical asymptote. So we have the left and the right bound both approach infinity or negative infinity, or one goes negative and one goes positive. Jump discontinuity is when we cannot remove the discontinuity just by filling a dot somewhere in a hole. In this case, there's a, you could say, a jump on the graph to the next part of the function. And if you're curious, this is called a step function or a floor function. So it just kind of truncates the decimal of whatever real value x is. Not super important for this lesson, but it highlights jump discontinuity, so it's in here. There it is. Probably never seen it before, have you? All right, so number one, we're going to look at these four different functions, a, b, c, and d, and we're going to talk about four different questions. So read the questions carefully. Number one says, function f has a removable discontinuity at x equals a. Please ignore the typo there. Which of the following could be a graph of f? So removable discontinuity means we can fill a dot to remove the discontinuity. And so this is definitely going to be D. I could put a dot right on this hole, and then the graph would be continuous. B and C, I could not add a dot or move a dot to remove the discontinuity because it'll be jump discontinuity for each of those. And for A, I can't add a dot because we have a vertical asymptote and this is an infinite discontinuity. So that's the first question. The second question says, the limit as x approaches a of f of x exists. Which of the following could be the graph of f? So to say that the limit as x approaches a exists means that the left side and the right side limits have to be equal. And so that's another way of saying removable discontinuity. So this is really a different way of asking the exact same thing we're asking in question A, or question 1. It's the exact same question. So we're looking for the graph with this removable discontinuity, and that would still be graph D. Question number 3 says the limit as x approaches a from the left and the limit as x approaches a from the right and f of a itself are all distinctly different numbers. So that means they're not the same number. They're all three different numbers, and neither of them are infinity because infinity is not a real number. It's a concept. So if the left and the right are distinctly different numbers, then we also know that the limit as x approaches a does not exist. And so if we look at our graphs for a, the limit as x approaches a from the left and the right both approach infinity. Infinity is not a real number, it's a concept, so it's not a. It is b. The limit as x approaches from the left is some positive number. The limit as x approaches a from the right is some negative number. And f of a itself is defined by the dot, which is yet another negative number. So they all three have different, the limits and the f of a itself are all different outputs. So they're all distinctly different real numbers. C does not work because we don't have a definition for A. We have two holes, but we have no dots. So A is not defined in this function. Or you could say it's not part of the domain. And that dot is really the only difference between B and C, is that we do have a definition for A in the B function, but we don't have a definition for A in the C function. D doesn't work. Not only do we not have a definition for A, but also the left bound and the right bound limits are equal. And the conditions are, they are distinctly different real numbers. So D doesn't work for both of those reasons. All right, number 4. Number 4 is a very tricky question. And it's only tricky because of the last 3 words in the sentence. Which of the following is or are continuous on the domain? So is or are means maybe there's more than one answer. And on the domain, so this changes the answer to the question, these 3 words right here. So that means if you look at just the domain of each function, as in only when the function is defined, are those chunks of the function continuous. So let's consider what the domains of each of these functions are real quick. In function A, the point x equals a isn't defined. We don't have, as in we don't have a definition for a. It's not part of the domain for this function. So we write our domain as negative infinity to a, but not including a, in unison with a, but not including a, to infinity. B, we have everything below a, everything above a, but then because of this dot, we also have a defined. And so the domain for this one is any number, any value of x we have a definition for. And so there's no value of x that we would call undefined because they're all accounted for. So domain is all real numbers for B. C, like D, doesn't have a definition for A, and D as well doesn't have a definition for A. So C and D would have the same domain as A, from negative infinity to A and from A to infinity, but not including A. If it was including A, we would have the square brackets on A, either in one spot or the other. And so if we look at just the domains, which of the following are continuous on the domain? So if we see the domain from negative infinity to A, this line is continuous. And from A to infinity, it's also continuous. So A would work because it is continuous within its own domain. B, its domain is all numbers. If you consider all the x values, it's definitely not continuous because we have jump discontinuity here. C would be a correct answer. Again, because its domain doesn't include A, you consider each interval of its domain. Each interval from negative infinity to A is continuous, and A to infinity is also continuous. So C would work. D would also work because A is not defined, so on each interval of the domain, our graph is continuous. Now, if you were to remove these 3 words from the question, if we just omitted them and just asked the question, which of the following is or are continuous, we would say none of them are continuous. None of them are continuous because we have discontinuity in each of the graphs at x equals a for one reason or another, whether it's removable discontinuity, infinite discontinuity, or jump discontinuity. So those last 3 words really do change the question a lot. And so if interval notation looks new to you, this is something you definitely want to brush up on and be familiar with. A couple examples. What are all values of x for which f has removable discontinuity? So to repeat, removable discontinuity means basically I can add a dot to remove the discontinuity. So at -2, I could put a dot on our graph to make this continuous. At +2, we already have a dot, so I could add a dot or just move the dot, and I could remove the discontinuity. the fact that this dot is down here doesn't really change that this is removable discontinuity. And then again at 3, we could add a dot here to remove discontinuity. So -2, +2, and 3 are my answers. For what values of x do we have infinite discontinuity? So basically we're looking for a vertical asymptote, and we have only one when x equals -3, so that's our answer. Our values of x for jump discontinuity. So basically if you were drawing this with a pencil, the only times you'd have to pick up your pencil and jump to the next spot, basically. So -1 we'd have to jump, and +1 we'd have to jump. So we have 2 points of discontinuity that are jump discontinuity. That's -1 and +1. A more formal definition for that is the jump discontinuity is when the limit as x approaches a from the left is not equal to the limit as x approaches a from the right. All right, those are our examples. Takeaways. We're now looking at the concept of continuity in the context of limit statements. We've seen 3 different types of discontinuities, and we're getting a little more familiar with the vocab around those as well.